So if we're talking about topographic mapping, um, we're gonna move ahead from this hill profile. Here we've got kind of an ancient way of describing topography, very descriptive, and to the extent that it's useful, easy to read. It isn't particularly measurable, doesn't tell you much about scale, but it tells a story, and that's what topographic mapping is all about. Let's come ahead in time a little bit, and this idea of Hatcher shading. And here we've got a vertical view. The planimetric detail would be shown in, um, for the time as accurate a position as possible, and then the topography is shown with this hatchering to portray some sort of upheavals in the surface. And I'm going over some of the older ways of looking at topography because some of them are going to come into play as we move forward in time. You can see how some of these things are used to portray things, even in some modern methods. Certainly this is a modern way of looking at it, but it's really almost an ancient method, and that being color shading. Different elevations have different colors. You've got a scale there. There's some sort of a blend from one color to the next as the elevation changes. There would be similar to the idea of contours, um, but this is more of a graphical representation without the accuracy, just showing that the trends in certain areas are higher or lower. So that's what the color shading. But color shading really comes into play when we start getting into GIS applications, because it's a very vibrant way, and we'll look at that as we go on. Now, light shading. We talk about the hill profiling, the hatchering. This light shading really, it's a way of taking the ground and trying to go back to some of that 3D effect, to give the perception that something is higher or steeper or at a different elevation. And you can see how that works out with the contour lines, how it blends when we're relating it to the contours themselves. And of course, speaking of contours, when we talk about topographic mapping, contours are typically what people are going to be talking about. Trying to portray the topography of a target area. Traditionally, contours are what is going to be used. They're readable, they're accurate. The placement represents an elevation. If we were to slice the ground at a given elevation, that line is what the slice would look like. So that anywhere along that line, you are very accurately portraying that elevation, as well as coordinate positions along that line. It's usually scale and view independent. The only consideration to scale is the smaller the scale, the closer the contours are going to get together, and the harder they are going to be to read. So with smaller scale photography, you typically, we're talking about paper maps, would be looking at larger contour intervals. But contours are just a way of visualizing um, what's going on. A way of showing how that topography is being changed as you go from one area to the next. Contours that are very close together shows that it's a steep hill. Um, contours point. If a contour turns back on itself, it's pointing upstream. Things like that. Sometimes it takes a little getting used to, a little practice in reading, but contours are a great way of visualizing, but they are just, in most cases, a way of visualizing something else, and that is the three-dimensional recording of the surface. You know, there's a lot of different ways of visualizing. Here we have a color photo with hill shading, very graphic, very representative, but you know, what is the elevation at any point in that photo? Contours are going to give you that elevation. So contours are a way of visualizing, but an accurate way of representing what's going on, but they are not the underlying data. You know, the underlying data is this three-dimensional surface that is being collected. If we were to, you know, here again we've got some light shading, some color shading, uh, and in this case we want to think about digital elevation models, or DEMs. We're also going to think about digital terrain models, or DTMs. Sometimes these terms are used interchangeably. Most people in common usage would refer to a DEM as a raster product, rows and columns, but the rows and columns are representing elevations. Now, in this case, what we're looking at is a digital elevation model. Okay, it's a rectangle of rows and columns. Each row and column has an elevation, but in this case, the elevation has been assigned a color value. So they really mix and match and work together in this idea of how to portray topography. Digital elevation models, we'll come back to uses of these in a minute. But digital terrain model, this is the raw data. This is what the photogrammetrist is actually going to sit there and collect day after day, point after point. Planimetric features that may affect the ground, for example, the edge of a road, those may show up in the topographic raw data. A driveway that changes the topography may show up in the three-dimensional data, or it could just be random points, you know, not lines that represent a break in the topography, but just random points out in the middle of a parking lot to show how the elevation changes for any given point. Once we have that digital terrain model, that the point by point collection, what we are going to do is use software, some sort of typically engineering software, that is going to create planes, three-dimensional, three-point planes in a triangular, for obvious reasons, irregular, again, fairly obvious. So we have a network of irregular triangles. And that is how the computer is going to see that surface. Anything that we do, any measurements that we make, any analysis that we do, whether it's flow or slope or elevation or volume, everything is going to be based on this triangular irregular network that is a joining up of those raw data points. So at that point in the process, creating contours just becomes a way of visualizing that underlying data. So from that network of triangles, the software is going to look at the edges of the triangles, find even elevation values, connect up all those even elevation values of, you know, of like value. So we're going to have 800 above sea level, all the 800 above sea level points. It's going to connect those up in a linear fashion and represent the ground with contours, but the surface is still where the power is. DEMs are great for visualization. DTMs are what we're going to use for the real analysis in an engineering, especially an engineering setting. Once we start getting into GIS, then the DEMs are a lot more prevalent because we're looking more for trends and not necessarily specific point data. Final product, if we were to take and combine the planimetric data with some sort of visualization of the topographic data, we've got a final product. In this case, a topographic map, and this is what where we would finally take this, convert it to some sort of a vector graphic format. AutoCAD would be a great example. In this case, this slide was made by taking that data and creating a postscript. The postscript just starts at 00 in the upper left-hand corner, like any other image format, and go to a certain point, draw a certain line, and color it in a certain way. If we're sending it to an engineering client, then they're going to look for state plane coordinates, very discrete point values, and then graphics attached in some way that is descriptive. Possibly a loopy green line to represent trees, a heavy purple rectangles to represent buildings, and then we transmit that to the client, explain what everything means, and the lines along with individual symbols become the basis of whatever analysis they are finally going to do, whether it's engineering, design, or making a base map for some sort of a larger geomatics or GIS type of project.